Chromium is a chemical element with symbol Cr and atomic number 24. It is the first element in group 6. It is a steely-grey, lustrous, hard and brittle metal which takes a high polish, resists tarnishing, and has a high melting point. The name of the element is derived from the Greek word chirōmu chroma, meaning color, because many of the compounds are intensely colored. Ferrochromium alloy is commercially produced from chromite by silicothermic or aluminothermic reactions, and chromium metal by roasting and leaching processes followed by reduction with carbon and then aluminium. Chromium metal is of high value for its high corrosion resistance and hardness. A major development was the discovery that steel could be made highly resistant to corrosion and discoloration by adding metallic chromium to form stainless steel. Stainless steel and chrome plating together comprise 85% of the commercial use. Trivalent chromium ion is an essential nutrient in trace amounts in humans for insulin, sugar and lipid metabolism, although the issue is debated. While chromium metal and Cr ions are not considered toxic, hexavalent chromium is toxic and carcinogenic. Abandoned chromium production sites often require environmental cleanup. Characteristics. Physical chromium is remarkable for its magnetic properties. It is the only elemental solid which shows antiferromagnetic ordering at room temperature. Above 38 degrees Celsius, it changes to paramagnetic. Passivation. Chromium metal left standing in air is passivated by oxidation, forming a thin, protective surface layer. This layer is a spinel structure only a few molecules thick. It is very dense, and prevents the diffusion of oxygen into the underlying metal. This is different from the oxide that forms on iron and carbon steel, through which elemental oxygen continues to migrate, reaching the underlying material to cause incessant rusting. Passivation can be enhanced by short contact with oxidizing acids like nitric acid. Passivated chromium is stable against acids. Passivation can be removed with a strong reducing agent that destroys the protective oxide layer on the metal. Chromium metal treated in this way readily dissolves in weak acids. Chromium, unlike such metals as iron and nickel, does not suffer from hydrogen embrittlement. However, it does suffer from nitrogen embrittlement, reacting with nitrogen from air and forming brittle nitrides at the high temperatures necessary to work the metal parts. Occurrence. Chromium is the 22nd most abundant element in Earth's crust with an average concentration of 100 ppm. Chromium compounds are found in the environment from the erosion of chromium-containing rocks, and can be redistributed by volcanic eruptions. Typical background concentrations of chromium in environmental media are: atmosphere and Lt 10 nanograms m-3, soil and Lt 500 mg kg-1, vegetation and Lt 0.5 mg kg-1, freshwater and Lt 10 UgL-1, seawater and Lt 1 UgL-1, sediment and Lt 80 mg kg-1. Chromium is mined as chromite ore. About 2/5 of the chromite ores and concentrates in the world are produced in South Africa, while Kazakhstan, India, Russia, and Turkey are also substantial producers. Untapped chromite deposits are plentiful, but geographically concentrated in Kazakhstan and southern Africa. Although rare, deposits of native chromium exist. The Udachna pipe in Russia produced samples of the native metal. This mine is a kimberlite pipe, rich in diamonds, and the reducing environment helped produce both elemental chromium and diamond. The relation between Cr and Cr strongly depends on pH and oxidative properties of the location. In most cases, Cr is the dominating species, but in some areas, the groundwater can contain up to 39 micrograms micrograms liter of total chromium, of which 30 micrograms liter is Cr. Isotopes. Naturally occurring chromium is composed of three stable isotopes, 52 Cr, 53 Cr and 54 Cr, with 52 Cr being the most abundant. 19 radioisotopes have been characterized, with the most stable being 50 Cr with a half-life of 1.8 times 1017 years, and 51 Cr with a half-life of 27.7 days. All of the remaining radioactive isotopes have half-lives that are less than 24 hours and the majority less than 1 minute. This element also has two metastates. 53 Cr is the radiogenic decay product of 53 Mn, and chromium isotopes are typically collocated with manganese isotopes. This circumstance is useful in isotope geology. Manganese chromium isotope ratios reinforced the evidence from 26 Allen 107 PD concerning the early history of the Solar System. Variations in 53 Cr, 52 Cr and Mn Cr ratios from several meteorites indicate an initial 53 Mn 55 Mn ratio that suggests Mn Cr isotopic composition must result from in situ decay of 53 Mn in differentiated planetary bodies. Hence 53 Cr provides additional evidence for nucleosynthetic processes immediately before coalescence of the Solar System. The isotopes of chromium range in atomic mass from 43 U to 67 U. The primary decay mode before the most abundant stable isotope, 52 Cr, is electron capture, and the primary mode after is beta decay. 53 Cr has been posited as a proxy for atmospheric oxygen concentration. Compounds. Chromium is a member of group 6 of the transition metals. Chromium has an electronic configuration of 4s13d5. Owing to the lower energy of the high spin configuration, chromium exhibits a wide range of oxidation states, with +3 the most stable. The +3 and +6 states are the most common in chromium compounds, while +1, +4 and +5 are rare. The following is the Purbeck's diagram for chromium in pure water. Perchloric acid as sodium hydroxide. Chromium. A large number of chromium compounds are known. Chromium can be obtained by dissolving elemental chromium in acids like hydrochloric acid or sulfuric acid. The Cr3+ ion has a similar radius to Al3+, and they can replace each other in some compounds, such as in alum and alum. When a trace amount of Cr3+ replaces Al3+ in corundum, pink sapphire or red-colored ruby is formed depending on the amount of chromium. Chromium ions tend to form octahedral complexes. The color of these complexes is determined by the ligands attached to the Cr center. Commercially available chromium chloride hydrate is the dark green complex Cl. Closely related compounds have different colors: pale green Cl2 and violet Cl3. If water-free green chromium chloride is dissolved in water, the green solution turns violet after some time as the chloride in the inner coordination sphere is replaced by water. This kind of reaction is also observed with solutions of chrome alum and other water-soluble chromium salts. Chromium hydroxide 3 is amphoteric, dissolving in acidic solutions to form 3+, and in basic solutions to form Cr6 3-. It is dehydrated by heating to form the green chromium oxide, a stable oxide with a crystal structure identical to that of corundum. Chromium compounds are powerful oxidants at low and neutral pH. Most important are chromate anion, Cro2-4, and dichromate anions, which exist in equilibrium, 2,2- plus 2H plus 2- plus H2O. Chromium halides are known also and include the hexafluoride CrF6 and chromyl chloride Cro2Cl2. Sodium chromate is produced industrially by the oxidative roasting of chromite or with calcium or sodium carbonate. The dominant species is therefore, by the law of mass action, determined by the pH of the solution. The change in equilibrium is visible by change from yellow to orange, such as when an acid is added to a neutral solution of potassium chromate. At yet lower pH values, further condensation to more complex oxyanions of chromium is possible. Both the chromate and dichromate anions are strong oxidizing reagents at low pH. Cr2O2-7 plus 14H3O plus 6E-2 Cr3 plus 21H2O. They are, however, only moderately oxidizing at high pH. Cro2-4 plus 4H2O plus 3E- Cr3 plus 5O- chromium compounds in solution can be detected by adding an acidic hydrogen peroxide solution. The unstable dark blue chromium peroxide is formed, which can be stabilized as an ether reduct Cro5 or 2. Chromic acid has the hypothetical formula H2CrO4. It is a vaguely described chemical, despite many well-defined chromates and dichromates being known. The dark red chromium oxide Cro3, the acid anhydride of chromic acid, is sold industrially as chromic acid. It can be produced by mixing sulfuric acid with dichromate, and is a strong oxidizing agent. Chromium and chromium. The oxidation state +5 is only realized in few compounds but are intermediates in many reactions involving oxidations by chromate. The only binary compound is the volatile chromium fluoride. This red solid has a melting point of 30 degrees Celsius and a boiling point of 117 degrees Celsius. It can be prepared by treating chromium metal with fluorine at 400 degrees Celsius and 200 bars pressure. The peroxychromate is another example of the +5 oxidation state. Potassium peroxychromate 4 is made by reacting potassium chromate with hydrogen peroxide at low temperatures. This red-brown compound is stable at room temperature but decomposes spontaneously at 150 to 170 degrees Celsius. Compounds of chromium are slightly more common than those of chromium. The tetrahalides CrF4, CrCl4, and CrBr4 can be produced by treating the trihalides CrX3 with the corresponding halogen at elevated temperatures. Such compounds are susceptible to disproportionation reactions and are not stable in water. Chromium. Many chromium compounds are known, including the water-stable chromium chloride CrCl2, which can be made by reducing chromium chloride with zinc. The resulting bright blue solution is only stable at neutral pH. Many chromous carboxylates are known, most famously the red chromous acetate 4 that features a quadruple bond. Chromium. Most Cr compounds are obtained by oxidation of electron-rich octahedral Cr complexes. Other Cr complexes contain cyclopentadienyl ligands, as verified by X-ray diffraction of Cr. Cr quintuple bond PM has also been described. Extremely bulky monodentate ligands stabilize this compound by shielding the quintuple bond from further reactions. Chromium. Many chromium compounds are known, Most are derivatives of chromium hexacarbonyl or chromium. History. Chromium was discovered as an element after it came to the attention of the Western world in the red crystalline mineral chroma, discovered in 1761 and initially used as a pigment. Nearly all chromium is commercially extracted from the single commercially viable ore chromite, which is iron chromium oxide. Chromite is now the principal source of chromium for pigments. Weapons found in burial pits dating from the late 3rd century BC, Qin dynasty of the Terracotta Army near Xi'an, China, have been analyzed by archaeologists. Although buried more than 2,000 years ago, the ancient bronze tips of crossbow bolts and swords found at the site showed unexpectedly little corrosion, possibly because the bronze was deliberately coated with a thin layer of chromium oxide. However, this oxide layer was not chromium metal or chrome plating as we know it. Chromium minerals as pigments came to the attention of the West in the 18th century. On the 26th of July 1761, Johann Gottlob Lehmann found an orange-red mineral in the Beryozovskoye mines in the Ural Mountains, which he named Siberian red lead. Though misidentified as a lead compound with selenium and iron components, the mineral was in fact crocoite with a formula of lead-1-chroma. In 1770, Peter Simon Pallas visited the same site as Lehmann and found a red lead mineral that had useful properties as a pigment in paints. The use of Siberian red lead as a paint pigment then developed rapidly. A bright yellow pigment made from crocoite also became popular. In 1797, Louis Nicholas Vauquelin received samples of crocoite ore. He produced chromium trioxide by mixing crocoite with hydrochloric acid. In 1798, Vauquelin discovered that he could isolate metallic chromium by heating the oxide in a charcoal oven, for which he is credited as the discoverer of the element. Vauquelin was also able to detect traces of chromium in precious gemstones, such as ruby or emerald. During the 1800s, chromium was primarily used as a component of paints and in tanning salts. At first, crocoite from Russia was the main source, but in 1827 a larger chromite deposit was discovered near Baltimore, United States. This made the United States the largest producer of chromium products till 1848, when large deposits of chromite were found near Bursa, Turkey. Chromium is also known for its luster when polished. It is used as a protective and decorative coating on car parts, plumbing fixtures, furniture parts and many other items, usually applied by electroplating. Chromium was used for electroplating as early as 1848, but this use only became widespread with the development of an improved process in 1924. Production. Approximately 28.8 million metric tons of marketable chromite ore were produced in 2013 and converted into 7.5 mt of ferrochromium. According to John F. Papp, writing for the USGS, ferrochromium is the leading end use of chromite ore. Stainless steel is the leading end use of ferrochromium. The largest producers of chromium ore in 2013 have been South Africa, Kazakhstan, Turkey, India, with several other countries producing the rest of about 18% of the world's production. The two main products of chromium ore refining are ferrochromium and metallic chromium. For those products, the ore smell to process differs considerably. For the production of ferrochromium, the chromite ore is reduced in large scale in electric arc furnace or in smaller smelters with either aluminium or silicon in an aluminothermic reaction. For the production of pure chromium, the iron must be separated from the chromium in a two-step roasting and leaching process. The chromite ore is heated with a mixture of calcium carbonate and sodium carbonate in the presence of air. The chromium is oxidized to the hexavalent form, while the iron forms the stable iron 3 oxide. The subsequent leaching at higher elevated temperatures dissolves the chromates and leaves the insoluble iron oxide. The chromate is converted by sulfuric acid into the dichromate, 4FeCr2O4 plus 8 sodium carbonate plus 7O2 8 sodium chromate plus 2 iron 3 oxide plus 8 CO2 2 sodium chromate plus H2SO4 sodium dichromate plus sodium sulfate plus H2O. The dichromate is converted to the chromium oxide by reduction with carbon and then reduced in an aluminothermic reaction to chromium. Sodium dichromate plus 2CCr2O3 plus sodium carbonate plus CO. Cr2O3 plus 2Al aluminium oxide plus 2Cr. Applications. Metal alloys now account for 85% of the use of chromium. The remainder is used in the chemical, refractory, and foundry industries. Metallurgy. The strengthening effect of forming stable metal carbides at the grain boundaries and the strong increase in corrosion resistance made chromium an important alloying material for steel. The high-speed tool steels contain between 3 and 5% chromium. Stainless steel, the main corrosion-proof metal alloy, is formed when chromium is added to iron in sufficient concentrations, usually above 11%. For its formation, ferrochromium is added to the molten iron. Also, nickel-based alloys increase in strength due to the formation of discrete, stable metal carbide particles at the grain boundaries. For example, a Connell 718 contains 18.6% chromium. Because of the excellent high-temperature properties of these nickel superalloys, they are used in jet engines and gas turbines in lieu of common structural materials. The relative high hardness and corrosion resistance of unalloyed chromium makes it a good surface coating, being still the most popular metal coating with unparalleled combined durability. A thin layer of chromium is deposited on pre-treated metallic surfaces by electroplating techniques. There are two deposition methods. Thin, below 1 micrometer thickness, layers are deposited by chrome plating, and are used for decorative surfaces. If wear-resistant surfaces are needed, then thicker chromium layers are deposited. Both methods normally use acidic chromate or dichromate solutions. To prevent the energy-consuming change in oxidation state, the use of chromium sulfate is under development, but for most applications, the established process is used. In the chromate conversion coating process, the strong oxidative properties of chromates are used to deposit a protective oxide layer on metals like aluminum, zinc and cadmium. This passivation and the self-healing properties by the chromate stored in the chromate conversion coating, which is able to migrate to local defects, are the benefits of this coating method. Because of environmental and health regulations on chromates, alternative coating methods are under development. Chromic acid anodizing of aluminium is another electrochemical process, which does not lead to the deposition of chromium, but uses chromic acid as electrolyte in the solution. During anodization, an oxide layer is formed on the aluminium. The use of chromic acid, instead of the normally used sulfuric acid, leads to a slight difference of these oxide layers. The high toxicity of Cr compounds, used in the established chromium electroplating process, and the strengthening of safety and environmental regulations demand a search for substitutes for chromium, or at least a change to less toxic chromium compounds. Dye pigment. The mineral chrōma was used as a yellow pigment shortly after its discovery, after a synthesis method became available starting from the more abundant chromite. Chrome yellow was, together with cadmium yellow, one of the most used yellow pigments. The pigment does not photodegrade, but it tends to darken due to the formation of chromium oxide. It has a strong color, and was used for school buses in the US and for postal service in Europe. The use of chrome yellow declined due to environmental and safety concerns and was replaced by organic pigments or alternatives free from lead and chromium. Other pigments based on chromium are, for example, the bright red pigment chrome red, which is a basic lead chromate 2. A very important chromate pigment which was used widely in metal primer formulations was zinc chromate, now replaced by zinc phosphate. A wash primer was formulated to replace the dangerous practice of pre-treating aluminium aircraft bodies with a phosphoric acid solution. This used zinc tetroxychromate dispersed in a solution of polyvinyl butyral. An 8% solution of phosphoric acid in solvent was added just before application. It was found that an easily oxidized alcohol was an essential ingredient. A thin layer of about 10 to 15 micrometers was applied, which turned from yellow to dark green when it was cured. There is still a question as to the correct mechanism. Chrome green is a mixture of Prussian blue and chrome yellow, while the chrome oxide green is chromium oxide. Chromium oxides are also used as a green color in glassmaking and as a glaze in ceramics. Green chromium oxide is extremely light, fast, and as such is used in cladding coatings. It is also the main ingredient in infrared reflecting paints, used by the armed forces to paint vehicles, to give them the same IR reflectance as green leaves. Synthetic ruby and the first laser. Natural rubies are corundum crystals that are colored red due to chromium ions. A red-colored artificial ruby may also be achieved by doping chromium into artificial corundum crystals, thus making chromium a requirement for making synthetic rubies. Such a synthetic ruby crystal was the basis for the first laser, produced in 1960, which relied on stimulated emission of light from the chromium atoms in such a crystal. Wood preservative. Because of the toxicity, chromium salts are used for the preservation of wood. For example, chromated copper arsenate is used in timber treatment to protect wood from decay fungi, wood-attacking insects, including termites, and marine borers. The formulations contain chromium based on the oxide Cro3 between 35.3% and 65.5%. In the United States, 65,300 metric tons of CCA solution were used in 1996. Tanning chromium salts, especially chrome alum and chromium sulfate, are used in the tanning of leather. The chromium stabilizes the leather by cross-linking the collagen fibers. Chromium tanned leather can contain between 4 and 5% of chromium, which is tightly bound to the proteins. Although the form of chromium used for tanning is not the toxic hexavalent variety, there remains interest in management of chromium in the tanning industry, such as recovery and reuse, direct, indirect recycling, use of less chromium or chrome-less tanning are practiced to better manage chromium in tanning. Refractory material. The high heat resistivity and high melting point makes chromite and chromium oxide a material for high-temperature refractory applications, like blast furnaces, cement kilns, molds for the firing of bricks, and as foundry sands for the casting of metals. In these applications, the refractory materials are made from mixtures of chromite and magnesite. The use is declining because of the environmental regulations due to the possibility of the formation of chromium catalysts. Several chromium compounds are used as catalysts for processing hydrocarbons. For example, the Phillips catalyst prepared from chromium oxides is used for the production of about half the world's polyethylene. FACR mixed oxides are employed as high-temperature catalysts for the water-gas shift reaction. Copper chromide is a useful hydrogenation catalyst. Other use: chromium oxide is a magnetic compound. Its ideal shape, anisotropy, which imparts high coercivity and remnant magnetization, made it a compound superior to the gamma iron 3 oxide. Chromium oxide is used to manufacture magnetic tape used in high-performance audio tape and standard audio cassettes. Chromates can prevent corrosion of steel under wet conditions, and therefore chromates are added to drilling muds. Chromium oxide is a metal polish known as green rouge. Chromic acid is a powerful oxidizing agent and is a useful compound for cleaning laboratory glassware of any trace of organic compounds. It is prepared by dissolving potassium dichromate in concentrated sulfuric acid, which is then used to wash the apparatus. Sodium dichromate is sometimes used because of its higher solubility. The use of dichromate cleaning solutions is now phased out due to the high toxicity and environmental concerns. Modern cleaning solutions are highly effective and chromium-free. Potassium dichromate is a chemical reagent, used as a titrating agent. It is also used as a mordant for dyes in fabric.